Hello everyone, my name is Takahiro Harada from MD, and I'm going to talk about some ray tracing related research we are doing at our team and MD. So in this talk, I'm going to give a high-level overview of our ray tracing related R&D. The topics include geometric representation and improvements in the importance resampling techniques and volume rendering. After that, Orochi library and HipRT and Radenpro renderer. Okay, the first topic I'm going to talk about is multi-resolution geometric representation. This work started with a question like this. In ray tracing, do we always need to raycast against fine geometries? For some scenes, it could be just an overkill, like a scene where an object is very far away from the camera or any ray origin. If there is a way to reduce the algorithmic complexity of the raycasting using BBH, it would be great. If we look at a raster graphics build, people has been using LOD or level of detail, which requires both pre-processing and additional memory storage for these. However, having an explicit LOD is quite a lot of work. Therefore, we explored if there's a better way to realize this goal in the ray tracing context. Another problem associated with this is about the materials on the geometric representation. Simply filtering parameters do work well for simple material, like just having a constant albedo on the diffuse color. However, if your material looks something like this, then it does not work at all. Material with a complex material graph is really hard to pre-filter. And it is, at least this is not obvious what to do with it. And in this work, we propose a geometric representation which doesn't add any additional data structure nor pre-processing for the simplification for the geometry. It's just a logic you can put in your BBH traversal logic, which is super handy and great. We also propose stochastic material sampling, which does not pose any assumption on the materials we have in the scene. So we simplify, simply it works on any complex material you may have. Let's look at the geometric representation we propose. We use ABBs in BBH as a coarse approximation of the scene geometry. In BBH, we store ABBs in different resolutions, so it is a good fit for this. Here, we are showing a teapots in different LOD level. On the left, we have a finer representation, and as it goes on the right, the approximation gets coarser and coarser. This is already useful for some rays like occlusion rays, or rays we use for AO. However, it is not clear how we can apply this for other ray types we trace in path tracer, where we trace quite a lot of non-occlusion rays. And here's an example. So we have a camera or eye looking at the scene, and then from the camera we cast primary ray, and then from the shading point, we try to connect to light source. The orange dotted line in this illustration is an example of an occlusion ray. All we need from here is to check if there is an object which is blocking the ray or not. Therefore, we can use this geometric approximation very easy. And then when we cast a ray sampled from BSDF to make a path deeper, which is shown here as a blue dotted line, we need to know about the hit point in order to construct a path. The biggest problem is the material. What should we do for the material at the hit point? We have a solution for that. So, as I said, an obvious way would be storing filtered values, which only works for a simple material. And if there are complex material which has materials graph or procedure texture, it is not easy to filter material. One example is shown here, where you can see a procedural texture or procedural Voronoi texture on the teapot. We came up with a solution called stochastic material sampling, where we only store 2 integer values at each node at BBH to sample material of the node. It does not pose any restriction on the material which is used for that. So we can use it for anything, and we can filter material very well, as you are going to see in the next slide. In this example, where this teapot has this procedural Voronoi texture, and as you can see in the image at the middle, the border of each Voronoi cell gets smoothed as it goes to an approximation. With this, we can use this approximation to other array types as well. We integrated into our path tracer with which supports complex material network. So let's look at the result. Here we are showing 2 examples. The left column is the path traced result without using any approximation. The center is with approximation. The left is the difference between these two. On the street scene, which is shown on the top, it doesn't make any difference visually. As you can see, the difference image is completely black, but we just get some performance improvements, which is great. On the second example, where we have quite a lot of indexation effect, we can see some difference, especially at the floor where we see a lot of reflections. And it is true that this method does make some difference in the visual. However, we can see that it is doing pretty good job. So if I only show you the image on the center column, you may think this may be the difference. Yeah, there's no visible artifact, but yeah, the result is just a bit different. And then the computation time for raycasting decreased up to 12% for these test scenes, which is great. There's a bit more detail about the method when it comes to implementation, which you can find in this tech report we published. Okay, I'm going to talk about importance resampling and reservoir sampling related method next. Importance sampling was first introduced to graphics community by Talbot et al. In 2005, and reservoir sampling was first used in stochastic light cutting paper published at 2016. Then a spatial-temporal reservoir sampling paper which combined these techniques to make a direct immersion sampling technique. And this work was published at 2020, and this is getting popular these days. We worked on some improvements on these techniques, which I'm going to talk from now on. The first one is about world space spatial temporal reservoir reuse. Reservoir-based resampling is a great solution for light sampling because it allows us to efficiently sample from thousands of light sources. Also, the nature of the algorithm is really good fit for the GPU. The algorithm itself is a very GPU-friendly streaming approach. Therefore, it makes it perform very well on a GPU. Another benefit is that there's no pre-processing to use in this method, meaning that it is a very good fit for dynamic scenes. However, unfortunately, the original approach does not scale to sampling lights at the secondary path vertices. This is because the reservoir they built is screen space. Therefore, if you have a secondary path vertices, you may not be able to look up the information. Therefore, this method was limited to path vertices directly visible from the camera or primary vertices. If this method is working very well for direct immersion, we should be able to extend it to indirect immersion as well. I think this is a natural extension, and this is the motivation of the work. In this work, we extended that and then used world space data structure. What we propose here is an adaptive world space reservoir cache using spatial hashing. We quantize the world space position based on an adaptive cell size and hash it. The hash function can collide, therefore, we resolved it by adding linear probing. After hashing the information, we create a list of reservoirs for every hash cell. This allows us to efficiently desample from many neighboring reservoirs in the world space. Therefore, it is not limited to the vertex visible directly from the camera. We can find nearby reservoirs in a single hash lookup. Here, we use jitter sampling to avoid the artifact coming from the hash quantization. In this way, neighbor path vertices can share the effort, which results in a better light sampling for global retention. Here we show how effective it is. On the left, we show the baseline where we simply do our next event estimation at 1 SPP, or 1 sample per pixel. Note that we are not showing the direct illumination component, but we are only showing the indirect illumination component. And then this scene is a bit challenging because there are a large number of light sources there. So there are more than 30K area lights in the scene. The image on the left is very noisy, so we can barely see what's going on. With the same ray budget, if we apply the method, we can get an image on the right. This is very obvious that the convergence is far improved compared to the previous, to the naive method or baseline. Now we can see that it is this kind of street scene, so it is great. And here is another example. Again, on the left, we are showing the naive or single SPP NE result, which doesn't show us anything, but yeah, with the method, we can see the information clearly on the right. Okay, then the next topic is about reservoir sampling related improvement, but yeah, we do what we propose is tiled reservoir sampling for many light rendering. Although using reservoir sampling improves the convergence as we saw in the previous slide, the effectiveness depends on the quality of the initial candidate samples. If we sample from bad samples, we do not get any good sample. Uniform sampling was used in the past, which is not good at all, especially under the situation where light importance varies a lot. One example would be like a case where we use VPL, where if a VPL is close to the shading point, the importance is going to be very strong. So the question is, how can we improve the initial candidate quality, or what is an efficient sampling technique we can use for this? We realized that by applying a technique called stochastic light culling, which we studied a while ago, this was a perfect fit for this purpose. I cannot go into the detail about the detail, but this makes it possible for us to use light culling without introducing any darkening bias. Here, we are assuming that we do desampling in the screen space, so we can do light culling for each tile using the random light range we define for each light sources. What this does is essentially applying a Gaussian roulette in another form, and then we can generate the candidate list with higher importance efficiently, and it is going to improve the convergence as I'm going to show later. However, if you simply apply stochastic light culling, it produces quite a lot of correlation of variance between adjacent pixels. To reduce the variance, we can de-interleave pixels as proposed by Segoviat et al. In 2006. Specifically, we split a single screen into subregions, then in each subregion, we process up to 1024 candidates. This not only helps to reduce the visual artifact by correlation, however, it does improve the memory access pattern as well, so the cost of this computation is reduced too. The image at the bottom or in this slide is an illustration of the process. So we start with a gbuffer and then we tile it and then we interleave into small region like that. And then we do the writing in this like the interleaved form, and then after that we do reconstruction or shuffling the pixels back to the original order. Here we are showing the improvements from the previous method or proposed method. As you can see on the left, the previous approach, which is a simple random sampling, is producing quite a lot of noise. However, as you can see that our method in the middle is producing cleaner image. The image on the right is with additional randomness to the interleaving pattern, which helps to reduce the visual artifact or correlation further. It produces far better results. Also, note that the computation time decreased due to the coherent memory access, so there is no reason not to use this technique for light sampling here. The next topic is about volume rendering, and then this is stochastic light culling for volume rendering. Okay, volume rendering is essential to add a realism to a rendered image. Example of a volume effect are light shafts, obviously, and fog effect. Also, volume scattering on primary day is way more visible and important comparing to volume scattering on deeper passes. In the literature, tree-based light sampling is often used when rendering under many light sources. Because of the nature, we need to maintain an acceleration structure for light sampling, which could be a burden sometimes, especially for real-time application. Then, a question we had when we started this research was that, is there a lightweight light sampling technique we can use for if we only apply volume scattering on primary days? An obvious choice here could be a light culling, which is very popular in real-time application. However, this is not very good because it culls light to reduce the computation cost. It is good because it culls light to reduce computation cost. However, it is not good because it introduces a darkening bias. On the other hand, the stochastic light culling, which I mentioned in the previous slide or previous topic, is a good fit for this purpose because it does not make the rendering darker while we can still cull light sources which doesn't affect much to the pixel. In the past, this stochastic light culling was only used for surface lighting, and in this work we extended it so that we can apply for volume rendering. So comparing to an application to a surface immersion, the situation is slightly different when we use it for volumes because we need to integrate, what we need to do is integration on the ray segment rather than integration on a point. Therefore, in order to compute the importance, we need to do a ray sphere intersection as shown here and then compute the range of the overlap of the ray to the sphere, then integrate importance on the range. This is a bit more in the detail, but we need to do an overlap test against two bounding spheres as the follow function of the light source is not a single smooth function anymore if we apply stochastic light culling. In this paper, we formulated the importance calculation for three cases. First one is there is no intersection between the ray and the spheres, and then the second case is intersection to the outer sphere, but not intersecting to the inner sphere. The last option is intersecting to both spheres. And then we integrate the importance of these areas or segments and then apply proper importance sampling technique for each case. Now, with this method, we can bound a light source to a spherical geometry, then we can cut light sources very easily. In order to achieve that, we used screen space tile cutting as done in the previous topic. Nice thing about this is that there is no additional data structure is needed, which simplifies the rendering pipeline and things quite a lot. Here is the result of the method. We did an equal time comparison. The images except for the reference image, which is shown on the right, were rendered in 1 second. We used reservoir sampling as a baseline, which is shown on the left. Our method is shown on the middle, and this is again an equal time comparison. As you can see, the noise level is reduced quite a lot comparing to the naive method in our method. And then, yeah, of course, this is not biased, so it converges to the reference image if we run longer. And this work is going to be published as a Eurographics short paper this year, and you can find more detail about the method in the short paper we are going to present there. Okay, let's switch the gear a bit. So far, I have talked about research project we have been working, but from here, I'm going to talk about some libraries and SDKs we are working on. The first one is this Orochi library. And this is a library we built to make our life easier to have multiple vendor support in GPU compute. AMD has been developing a HIP programming language actively for a while, and NVIDIA has CUDA programming language. Their APIs are very similar. However, developers need to maintain two different backends separately. We think this is nothing but just a complication a developer does not need to worry about. Therefore, we implemented this Orochi library to make it easier. So with this Orochi library, it let us only maintain a single source code and switch backend at runtime anytime if we need. Orochi loads DLL at runtime, so no linking to any specific libraries are required at compile time. This manages the devices you have on your system automatically. I'm going to talk about the detail later in the presentation. And then, yeah, if you ask for the number of devices you have, if you need to write CUDA and HIP code by yourself, you have to run these two APIs. But like if you use this Orochi library, you can simply ask for the library, hey, how many devices you have on the machine, and it is going to return the total number of devices you have on the system. So if you have single AMD GPU and single NVIDIA GPU, it is going to return 2. And then making a context on the device is very simple. You just need to tell the library that, hey, I want to make a context on device 1. And you do not need to think about if this is an AMD device or NVIDIA device at all. The Orochi library is open source, which you can find here. We have not implemented all the APIs yet, but the core ones we need are already there, so you can use it today. Okay, let's look at the library, or let's look from the perspective of the user. So let's say you are using CUDA today, CUDA API today in your application. The application looks something like this. So you have your code, which is shown on the box on the left, and then your code is calling CUDA API. In order to use this Orochi library, it is very simple. This is because the APIs are one-to-one correspondence from CUDA to Orochi. So you just need to swap the CUDA API to Orochi API. That's all you need to do. Then you put this Orochi library in between your application and CUDA API, and then your application runs as it is on NVIDIA GPU. However, it can also give you an option to execute your application on AMD GPU. The architecture of the library looks like this. This is something I showed in the previous slide. So user calls Orochi API, which redirects to HIP or CUDA API depending on the device. And here is a sample code enumerating the device and creating a context for each. One interesting thing is that if you ask for the device count on your machine, as I said, it is going to return the total number of GPUs you have. So, and then after that, you can set an argument like a HIP or CUDA to check how many AMD GPU or how many NVIDIA GPU you have on your system. And once you got the number of devices you have, then you can simply go through them, create a context for each device. Orochi checks the vendor of the device and create a context accordingly. So yeah, again, you do not need to worry about, okay, whether this device is AMD device or NVIDIA device. All right, so the next library I'm going to talk about is HipRT. This is a brand new library and brand new ray tracing API for HIP. The background of this work is that RDNA2 GPU we have released a while ago have a hardware accelerated ray tracing, which is exposed to DXR and Vulkan APIs. So if you are writing application on these APIs, you can use it. However, if you are writing your code in HIP, then you do not have an access to hardware ray tracing. HipRT solves the problem. HipRT is a library we have been working on, and it lets users to use the true power of RDNA2 GPUs. This is the first time we release it to the public, and this is released in this March 2022. HipRT implements ray tracing with BPH. It not only has a single way of building BPH, but we provide several options for users to choose what they need. If you need a faster build of the BPH, but if you are okay with a bit slower ray tracing speed, there's an option for that. And then if you need a faster ray tracing, but if you are okay with slower BPH build, yeah, there's an option for that. And this is designed to be scalable. And obviously, hardware ray tracing acceleration is here too. We designed the HipRT for general purpose. It can be used for both offline and online or real-time application. The primitives we support are triangles. Also, you can put your own custom primitives by defining your intersection function. You can use it for a scene with motion blur too. We support dynamic geometry by providing a BPH update API. At this first release, we only released a binary which works on AMD GPU, but we are going to enable execution on NVIDIA GPU too. This works on Windows and Linux OSs. We designed the APIs so that it can be lightweight and expressive. More specifically, it has a minimalistic setup and low level, so you can take control of your logic. It is designed to be performant, that's why we wrote it in a low level, so it has a very thin driver layer comparing to other ray tracing APIs. It is very easy to use, in my opinion, and yeah, this one is written in modern C++ standard. Let's look at the API example. On the left, you can find the host code APIs. For a single triangle mesh, you make a triangle mesh primitive by providing buffers, so we can read these in HipRT. Then we create HipRT geometry written in the middle. The input is the range of the input is a triangle mesh primitive we just created. And then after that, you can pass the HipRT geometry to your kernel. That's all you need to do to the host side. Device code example is shown on the right. It is just a HIP kernel again. and you do not need to write any special type of kernel. All you need to do is just pass the object you created in the host API, like HipRT geometry or HipRT scene if you create scene on top of the geometry. And then as you can see in this example, we are passing the HipRT, hip ray tracing scene, HipRT scene in the first argument. Then in the kernel, you simply create HipRT ray for the member variables, then create this HipRT scene traversal closest object, which keeps the state of the traversal. Then when you call this get next hit in the next line, it is going to find and return the next hit, which you can use it for the next step. For example, if you are writing a path tracer, you can use it for shading. As this is a closest hit operation, the hit returned by this function is the only hit it returns. We also have any hit which returns a hit found during the traversal. Okay, the last topic I'm going to talk about is about Radeon Pro Renderer. So Radeon Pro Renderer, which we have been working on for a while, is a photorealistic renderer. And here is a list of features we added recently. In addition to photoreal mode, we added toon shader and contour rendering mode, which makes it possible to mix non-photorealistic objects in photoreal rendering, as you can see here on the image on the top. This is very interesting because some materials are regular material, as we can see in the photoreal renderer, like the glossy floor there. However, it is mixed with this stylized small cute car. This allows us to make a very interesting image. And also, we added a colored shadow and cutting planes, which is very handy feature for visualization of complex object. And this feature is requested by CAD applications. We added an atmospheric volume, which is a faster way to realize light shafts and fog effect. And now we support primitive variables, which is also a very useful feature. You can put an arbitrary value on the primitives. One example is shown here on the image on the right. There are a few bunnies falling from the top and then deforming using finite element method simulation, which outputs the stress value per vertex. And then it is stored, this pressure or stress is stored as a print bar or primitive variables and passed to the shader. We could realize this with the existing feature. However, having this primitive variable makes the setup very easy, and you can make a very complex material or interesting look very easy. This is one of my favorite features we added recently. Also, we have been supporting CryptMath in the past. However, in this round, we extended so that it can capture secondary visibility in the CryptMath. One example is shown here. The left image is the rendered image. And then let's say we want to recolor the white chess pieces we see at the middle, which is visible from reflection and diffraction. The matte you see in the middle is improved CryptMath we implemented in this release. It captures these visibilities and then we can use it to recolor the image more naturally. So the recolored image is shown on the right. So the white chess piece is now gray, and if you look carefully, you can see that the chess piece through diffraction and diffraction are also gray. So it allows us to do this kind of like natural recoloring. This was something we couldn't do in the past with the previous CryptMath implementation. So that's a huge improvement. And we also made a LAMP node more flexible so that you can connect any shared network for each input for the LAMP node. And at last, we did a big change in the engine recently. So we have been using OpenCL for the compute language since we started the project. However, we did implement all the code in HIP now. We are very excited to announce that we added this HIP support in RPR. This is not finalized yet, but it is very close to the final. The day when we can completely switch to HIP backend is very soon. Okay, this is all I have today, and the topics I covered today are geometric representation and improvements in the importance resampling techniques. After that, I talked about some volume sampling technique, and then I introduced a bunch of like SDKs and libraries. Orochi library, which makes your life easier to run, keep your code running on AMD and NVIDIA. And also HipRT, this is a new ray tracing library which is written in HIP. And then I gave an update in Radeon Pro Renderer. Here are some references you can check for further information. Of course, in this short presentation, I couldn't go into the detail, but yeah, the detail can be found in these papers. And most of the information I presented today can be found at GPO website, so please visit there. And then we have a publication page where we list publication we did in the past. At last, I would like to thank all of my colleagues who worked hard on this project I presented today. And this is a disclaimer, and thank you for watching my presentation, and I hope to see you in person soon.